One of the ways to understand how a dynamic system behaves is to apply a step input and observe the output. This is called the step response. In engineering, the step response provides critical insight into how a system transitions from one steady state to another. This is especially useful because many real-world inputs such as switching on a voltage, applying a force, or opening a valve can be approximated as step inputs. The general form of the equation for a second-order mechanical system can be converted into a normalized form using the natural frequency and damping ratio. The function U represents a step function. Depending on the value of the damping ratio, we observe different types of response. First, in the overdamped case, the system returns to equilibrium without oscillating, but the response is slow. Mechanical brakes or systems with high friction are typical heavy damping. Second, critical damping represents the borderline case where the system returns to equilibrium as quickly as possible without overshooting. This is ideal in systems where we want fast response but no oscillation, like in precision measurement instruments or some suspension systems. Lastly, in the underdamped case, the system responds with oscillations that gradually decay over time. The amplitude decreases exponentially, and the system eventually reaches a steady state. Time-dependent study can be used to simulate a step response. Today, we will learn how to build a COMSOL model to simulation the step response of a cantilever. In a COMSOL simulation, we can define a step input function under the definitions node. By applying this step function to a boundary load, we can observe various system responses depending on the level of damping, as shown in the graph on the right. We will cover the following objectives in our time-dependent simulation of a cantilever beam's mechanical response to a step input. Time-dependent study: how to simulate the mechanical response of a structure when subjected to a step input. Defining a step input: the process of defining a step input force. Auxiliary sweep: performing a parametric sweep to study the effect of varying damping coefficients. Post-processing: how to visualize the results and compare different damping scenarios in a single graph. For the geometry, we continue using the same cantilever structure with dimensions of 100 micrometers by 10 micrometers. In the parameters section, we define key values such as length, width, and thickness, as well as external pressure and Rayleigh damping coefficients. To use a step input, we first define step function under the definitions node. Set the location parameter so that the step occurs at 5 microseconds. Next, create an analytic function and enter the step function in the expression field. Define the argument, time range, and function name as needed. Finally, click the plot button to visualize the input function. Next, under the solid mechanics node, apply the external pressure to the boundary load. The mesh settings remain the same as in the previous model file. In the time-dependent study node, specify the simulation time range and the time steps at which the solution will be stored. Next, to perform a parametric sweep, click on Auxiliary Sweep and configure the parameters as follows. Once the simulation is complete, you can go to the 1D plot group and select the result variable corresponding to the parameter to visualize the output. Let's get started.